Yo, what's up, dudes? My name is Kevin, and today I'm going to help you learn about the quick find and disjoint set data structure. It was in your first project, and a lot of people have questions about it, so I thought I'd make a quick video explaining how to do it and what the algorithm really does. So, without any further ado, I think this PowerPoint that your discussion TA gave was really good. Hassan Whiteside. No, I was kidding. His name is Hassan something. It's not Whiteside, but so your union find data structure. So let's say you have like 5 objects. In this case, they're computers. And you want to know if they are connected. It doesn't matter how you connect them, just any way to get them connected. For example, if you draw a line from computer 1 to 2, can you get to computer 3 from 1? There's no way because there's no connection. But if it's set up like this, can you send data from computer 1 to computer 5? And you can because there's a line going from 1 to 3, from 3 to 4, and 4 to 5. So here you couldn't go from 1 to 3 because there was no line here. There's no connection. But in this case, there was a connection. And it doesn't matter that's going through things. So that's the key of this algorithm. You don't really care how far apart you are from something. You just care if it's possible to reach that other point. So you can think of further application of this. You can think of maybe cities and routes, or people like friendship. This guy's a friend of that guy, who's a friend of that guy. There's almost infinite applications for this. It's a very basic data structure that's used all over. So in this case, let's say you connect computers 1 and 2. So if you connect 1 and 2, and they ask you, is 1 and 3 connected? That's false, because only 1 and 2 is connected. But can you connect from 2 to 1? Yes. So then let's say you draw this line in, 3 to 4, and then this line here, 4 to 5. Can you go from 3 to 5? Yes. And let's say you connect 1 to 4. Can you go from 1 to 5? You go all the way down. So you can play around this and see how it works, but the general idea is if there's a line connecting two things in any possible way, then they are connected. That means there's a path. So what that means for you is, let me go to Paint and let me see my drawing skills. Okay, that's a somewhat decent circle. And let's get 5 of them. Okay, so I have 5 circles, and I'm just going to write in them real quick. So actually, I want a paintbrush. 1, 2, 3, 4, and 5. Okay, so here's my 5 circles. Terrible penmanship, but if I say connect circle 2 to circle 1, what I'm gonna do is I'm gonna move 2 right below 1, and I'm gonna connect it. Now, if I say connect 4 to 3, what I'm gonna do is I'm gonna move 4 right below 3 and connect it like this. And if I say connect 5 to 4, for example, what I would do is just bring 5 down here and connect it. So there are so many ways you could program this. You could do it with a stack, you could do it with a tree, you could do it with arrays, you could do it with 2D arrays and make an adjacency matrix. But for this purposes of this assignment, since it was very simple, the easiest way was just with an array. So I'm going to start with, this is the most basic algorithm, and we're going to talk about this. And then after that, we'll talk about path compression and a little bit of weighting heuristics that make it a little more optimized and give you a little better big O notation. So the general idea is that, as I did here, if I say connect two things, you make a connection between them. Very obvious, almost semantics there. But how you make that connection really depends on what programming structure you have. And since I said arrays are the easiest one, I'm just going to talk about arrays. So let's say you make an array. What should I use to make an array? Okay, so let me section this off a little bit. So this is your array that you're going to use for this. 1, 2, 3, 4, 5. Okay, well, the sizes are a little bit off, so you're going to have one gigantic one. So here's the element 0. Watch my mic for a sec. So there's like element 0. Then let's draw element 1, 2, 3, and 4. So you'll notice that this is the 0th index. The 0th index actually corresponds to the first one. So the first one actually corresponds to the value of 2. The third one actually corresponds to the value of 4. The fourth one actually corresponds to the value of 5. So for whatever your index I, it actually represents I plus 1. So index I represents I plus 1. This is the actual value, and this is the index. So I'll write that into value and index. Okay, so you have your index and your value. And what this array, so we're going to say like array at I. Array at I is going to be equal to whatever it's connected to. So in this case, 1 isn't connected to anything, so we can just put itself in there, 1. In this case, 2 is connected to 1, so we're going to put a 1 here also. Here, we see that 3 is connected to itself. So also, the way you store it, you can store it based on index, or you can store it based on the value. So I'm storing it based on the value, but you could also store it based on index. So for example, if you had a 0 here, that's also perfectly acceptable. If you had a 0 here, that's also perfectly acceptable. It all depends how you program it, as long as you're consistent. So for the next one, 2, which is the third one, it's only connected to itself, so I'm just going to write a 3 here. Now for index 3, which represents the fourth object, it's connected to the third object, so I'm going to put I'm going to put 3 here. And for the fifth object, which is represented by I equals 4, is connected to the fourth object. So to see if something is connected, what you do is, if I want to say, is 5 connected to 3? First you go to the fifth object, which is right here, and you can see that it's connected to 4. So then you go to 4, which is the third one, and see that's connected to 3. So you traverse up this and you find out that the root is 3. Now, that's pretty slow, so we're going to show you some ways to speed this up. The first way is path compression. I'll talk about that one first. So, actually, let me leave all these things. That's fine. I'm going to take this 5 here, and instead of having it connected to 4, which is connected to 3, it's really slow to go all the way up. So what I'm going to do is I'm going to move this over here, and I'm going to connect the 5 directly to the 3. Bam. This is what's called path compression. And you might not think it's a big deal right here, but if I had like 10 nodes, for example, like this, and there's lines going between each of them. Boom, boom. All right. So to go from here all the way up there takes a long time. You have to go 1, 2, 3, 4, 5. It'd be so much more efficient if you just had one node here and everything connected to it. So if I had a bunch of little circles here and everything was connected directly to it. This is the kind of implementation you want. This is what's called path compression. So path compression is good because it helps you find the root faster, and the root is the key. So if you want to compare if two things are connected, the long way is comparing every single connection, seeing every possible path if you can reach the other one, which at minimum is n squared time probably. So that's not good. It's a lot better if you can go directly to it in one step. This is like one. So if you find the root, you can compare roots. For example, if I say, is 2 connected to 5? you get the root of 2, which is 1, and you get the root of 5, which is 3. Does 1 equal 3? No. Now if I say, is 4 connected to 5? You get the root of 4, which is 3, and you get the root of 5, which is 3, and you compare, does 3 equal 3? Yes. So 4 and 5 are connected, but 5 and 2 are not connected. And I guess the next important thing, actually let me just open a new one, is some kind of a weighting heuristic or ranking. So what that means is if I had something like this with 3, okay? So there's a root which has 2 things below it. Then I might have something over here with, let's say, 1, 2, let's say each of these have 2 also. And these circles are starting to become ovals, but you still get the overall idea. Boom, boom, boom. Just make connections. Right now, we don't really care what the values inside are, but to compare these two. Now, let's say, just to make this easier, let's call this node 1 and node 2. If I said connect node 1 and node 2, it's a lot easier to make a line from here to here than it is to do a line, like a directed line this way. It's a lot easier to do this than to do this. This is bad. We don't want to do this. The reason we don't want to do that is because we need to connect everything below it to 1. That's what path compression is. This one actually hasn't had path compression yet. All of these bottom ones here should be connected directly there. So path compression hasn't happened yet, but with path compression, all of these should be connected directly to the 2. So it's a lot easier to transfer everything to be connected to the 1 if you have lesser things to do, right? So instead of making 1 the new root and having all of these things point to 1, we can just make 2 the new root and just draw a line like this. Let me stop using red. So we do this, and then when we do path compression, both of these nodes can go directly to 2 also. And the reason this saves time is because here you're only connecting 3 things to 2, instead of here you're connecting 1, 2, 3, 4, 5, 6 to 1. Plus that, actually, 7. So connecting 7 things to 1, you can just connect 3 to 2. So it saves some time. It's pretty good. So this is weighting. It's like some kind of weighting heuristic. And over here we had path compression. So between path compression and weighting, that's how you solve this problem in minimal amount of time. And if you actually go to Google and just type in disjoint set or union find, anything like that, disjoint set and union find are the same thing, by the way. And you just scroll down, you can find in Wikipedia the exact solution. So if you look this up and you implemented this, that's exactly what you have to do. This is pseudocode. Obviously, you have to convert it into C++, but that is the answer. I'll show you the code that I created. So in my GitHub, source, you find, and main. Actually, I'll also show you my header just to give an idea what a header should look like. So I have my main class. My main class doesn't do much, actually. It just takes the input file, which in the end, I believe your professor wanted you to change it so you don't take an input file, you just take a stream, the standard in, cin. But initially, you had an input file. And if the operation was 0, I believe you had to connect them. If the operation was 1, you had to see if they were connected and print true or false, something like that. So the main, which was already almost given to you, is here. And I'll post a link to this GitHub. I have comments on almost every single line, so you can see exactly what I was thinking when I was coding this. And over here, okay, so a lot of people didn't know if you needed a header file or not, and you should always, always, always make a header file. Header files are extremely important. in C++, would recommend 10 to 10 make header file. So this is my header file. It's just all the functional prototypes of all the different methods I have or functions I have. So this is my constructor, unit find int num elements. Then I have find root, union, and boolean is connected. So I have three methods other than three functions other than my constructor and destructor. Do you need a destructor? Yes, always make a destructor. So I have these two global variables inside the scope that are private, int roots and int progeny. And int roots is for the basic thing, which is knowing what everything is connected to. And progeny is the weighting heuristic. You can call it rank, you can call it power, you can call it children, whatever name you want to put. But I usually name it progeny, but you can do it whatever you want. You can do whatever you want. So back here, let me show you my union find.cpp. Okay, so the most important method is actually the find root method. And what happens here is I find the root, but there's also path compression that happens simultaneously. This is recursive. So I say if the root's index is equal to the index, that means if the index is a root, then just return the root itself, return index. Otherwise, root's index equals find root's index. So I keep on going up and do path compression if it hasn't happened. The key is in this equal sign. And if you don't see this, you can just like look at my code longer and dissect it. There's comments on every single line. You can read it. But the key is right here. That performs path compression and finds the root. Performing union is pretty simple. If first, just like a little check to see if they're already connected. If they're already connected, you don't have to do anything, so you just return. But if they're not connected, you should determine which one has a higher rank, and you put the smaller one to the bigger one, because that's more efficient. And to do that, all you have to do is put a connection from here to here. What that really means is you're setting the root of 1 to 2. So what's really happening here, if I'm connecting 1 to 2, I'm setting the array at 1, which is actually 1 minus 0, or 1 minus 1, sorry. Because, the first element is actually the 0th position in the array. I'm setting that equal to 2, or depending on how you do it, you can also set it array at 0 equal to 1. I think I actually went for this implementation because it made more sense to me using indexes or indices, but you can do it this way too. Just don't get tripped up with the -1s and +1s, depending on however you do it. So I do that. And to determine if they're connected, this is a very, very simple method, or function, sorry, in C++. All you do is find the root of your first index, and you find the root of your second index. If they're equal, then you return the true. What that means is, if I say, are 4 and 5 connected? And the answer is yes. The reason it's yes is because they both have the same root. If you have the same root, you're connected. Is 2 and 5 are not connected because the root of 2 is 1, the root of 5 is 3. Does 1 equal 3? No, 1 does not equal 3. So if you have different roots, that means you're not connected. So this is a very simple function. If you have the same root, then you're connected. Otherwise, you're not connected. And my destructor is also very simple. I just free the memory. God bless. And my constructor I didn't mention, but this is also important, is that I instantiated it to the size of the number of elements I get. And the number of elements was passed in as the first thing in the file or the file stream that you get. So I instantiate the array to that size, and I fill it up initially where everything has 0 progeny because there's nothing connected to it. It has no children, has nothing pointing to it. And I set all the roots equal to themselves. Everything just points to itself. So this is my code. I'll post a link to this, and I believe the professor is going to write his own code actually. So you can look at that as well. But mine has comments on almost every single line. explaining pretty much everything. If you don't understand it, you can always send me an email. Check my email every hour or two, and I'll be happy to help. So, yep, I hope this helps a little bit, and that is Unified.